and gentlemen, I think we'll get underway. And I want to welcome you to Aircroft, one and all. It's one of the better turnouts for a speaker, so that's to this guy's hats off to you. This guy's back by popular demand. But let me just say, this is hosted by the Idea Club. That meets regularly here once a month. And I want to just have the loyal members of the Idea Club put their hands up so you can look around, and if you want to know more about the Idea
Loyal
Club,
members.
there's some fine examples of idea people in this room, so welcome. This guy is one of the people that are called overnight success. The kind of people that work for 30 years very, very hard and suddenly get acknowledged. And this is one of them. I'm going to just say a little bit more, but before I do, I'm going to need to switch around, and I just want to acknowledge that Jeff over here, Jeff Suchak, has brought this photo along of ice, right? Do you want to just say a little bit about it? But obviously it kind of is appropriate for the discussion tonight. And I want to thank you. That's one of Jeff's photos on the wall beside him.
Well, and it's interesting because as soon as I saw the photograph, which we need to reload, there we go, I said, wow, that's Cosmo. And it's named Cosmos. So,
Thank you for sending that along.
It does take us beyond.
The inner outer space.
Okay,
Outer
now,
Space 101.
just so to have a nice transition, I better get over to here. But Ian is an overnight success because he is a self-made man. He's had a passion for space and understanding the universe, and he has just done it. And now is co-director of a NASA website that he'll be telling you a bit about, and is preparing a second paper in a peer-reviewed journal in the subject. So he's one of about 1,000 people in the world that are focused outside of our galaxy, and you're gonna like what he has to say. So thank you. There are but at least 3 people in the room who have had little bits of you at our parties and said, I got to talk to this guy. So talk.
Well, thank you, everyone. I'm thrilled to turn out. This is really an honor for me. I can't thank you all enough for coming. Douglas, thank you for hosting this shindig. This is really exciting. I'm just going to hog the floor for about 15 minutes or so, and I don't want to hog it completely. If there's anything at any point that I say that is technical or is difficult to understand, what would really upset me is if you didn't just interrupt, just shut out. We don't need hands, we're not class, there's no exams, there won't be points scored afterward, but it would really break my heart if there was anybody left after tonight that said to me, gosh, I didn't understand either word you said or anything that we're saying. So please, it's an idea club, it's not about me, it's really about the ideas that we want to share. So in a nutshell, tonight we're going to see and go beyond our universe. In the next few minutes, we're going to show and tell all we can see, all we can say about what fact does lie beyond. All of it. In a nutshell, and that's Ian if you want. Why? Because we need this knowledge to define 2 important terms that have a big and immediate impact on all of us. Term number 1, infinity. Term number 2, boundaries, also known as limits. Now we need to define these terms regarding our universe, not only for our own individual lives and wonder and excitement and understanding, though that too is true. Tonight, we're also going to be talking about our global lives as human beings, living and working and playing together. Now, humanity faces some serious challenges. On the forefront of facing some of those challenges are some of the people right here in this room tonight. Thinking people like Mark, involved in providing food that we all need to live. And of course, Doug, defending the environment that we all need to survive. Well, my friends, our friends that I speak of are fighting a rear guard action. They're fighting a rear guard action because the smartest people on our planet have failed to define for themselves or others, in their own terms, the definitions of infinity versus the boundaries and limits that we all need to recognize and live within if we are to continue to live together. I regret to report that so too, the smartest people on the planet in my field, the study of our universe, they also have failed to define these terms. Well, no more, because tonight, my friends, we are going to be amongst the first people on our planet. More than, gosh, there's 24 people here when we wrote this script. I said over 12 people. All tonight, I swear to God, I'm going to agree once and for all on the exact definitions of infinity and the boundaries of space and time. Now, I promise it's going to be easy, simple. Me too. With this new agreement, we are all, at the very minimum, I guarantee, going to be better enabled to face the global challenges that we do face together. But further, I believe that in fact it is with this knowledge that we're going to save our souls. I honestly believe that this is the knowledge that we need to win our future. Now, you're already taking part in a great social experiment here, the Idea Club. Well, tonight, we're all going to be taking part in a great social and scientific experiment. So welcome to the Idea Club tonight, my friends. Is everyone ready?
Yeah!
Here we go. We're going to start, we'll figure out how to work this puppy. We're going to start with all we can see, as promised, and this is going to go very quickly.
Just the arrow.
As far as all we can see, looking from planet Earth, you walk right outside here, we're clear, and you all recognize this is the Milky Way galaxy in which we live, our home galaxy, the Milky Way. Now, where we're going tonight, not only beyond our Milky Way, beyond our own universe. First stop in this journey is these two nebulae, known as the Large and Small Magellan Clouds, and they're just satellite galaxies, really little baby galaxies that orbit the Milky Way.
So Ian, that should be visible from here on.
This is a photograph taken by Alan Dyer, great Canadian astronomer, from the Southern Hemisphere though, that's the only thing different about this, and clear as a bell to local ancient souls in the Southern Hemisphere.
Okay.
Clear as a bell. These are actually in fact two of the four objects beyond our Milky Way that you can in fact see with your own human eyes. And this, like I said, this is just taken through an icon. It might be Canon, but you know, completely visible, totally visible with human eyes. These are the first two objects you can see on the way. Now, looking though about 10, 13 times further, this is the first big Milky Way-sized galaxy that we come to. In fact, it's our sister galaxy, Andromeda. Really, this galaxy and our own Milky Way are kind of a pair, and it's believed that, in fact, if we were there looking back, this is what we would see of us. This is a big galaxy. Now, there's Andromeda's companion galaxy, much smaller object, but not much further away. And that is basically all we can see, all of it, in a nutshell, with our unaided human vision. All right, so let's skip forward to what we can see with the world's best telescopes, or the best telescopes out of this world, because this is the view from NASA's Hubble Space Telescope. This is, in fact, Hubble Ultra Deep Field. It is the longest exposure photograph ever taken, hundreds of hours. It's the deepest view ever shown and to date of really how much we can see at the visible limits of our universe. In fact, we're going to zoom in and I'll show you as we go 10x and zoom in toward this little red dot here, and then 100x, you can see in this picture the limits of our visible universe. Because what you're seeing in the center, that ERO, it's an extended red object. The point is, it's not a point, it's not a star, that's a galaxy. That galaxy is receding from our Earth, our own Milky Way, at 96% the speed of light. It is ripping out there fast. It is the farthest, an example, one example of the farthest galaxies that we can see with the best space telescope available today. And in fact, if you look beyond this, what you get is basically nothing, an inky blackness. Now I know you see some noise and pixelation, that's really a product, an artifact of the system that they're using, but believe me, beyond that is nothing. They call it, in fact, there's a term astronomers use for this, the cosmic dark ages. I don't want to get too technical, but I do want to point out, I promise we show all we can see, that's it, as of tonight, until the next generation of telescopes.
So when you say there's nothing out there, you mean there's nothing that we can see?
Not only is there nothing we can see, because to be honest, what happens at redshift 6, 96% speed of light, is there's a neutral hydrogen fog that gets in the way. And you just can't penetrate it. It's like a fog. They call it cosmic dark ages because it's a fog. I'll tell you for a fact, if what you're asking is, if we had a better telescope, could we see further? Hell no. You'd see a lot of little tiny, fainter, smaller versions of this galaxy right in the same area, but you would not see much deeper because of that fog. Because in fact, let's face it, you're talking 96% of the way to the ends of the visible universe. So you're pretty much covering not only all we can see, but in fact, all there is, if that's what you're getting at.
Would that be-
How do you know there's, if you can't see past it, how do you know there's that?
In a nutshell, we're measuring the redshift, the speed it's moving away from us at, and we know that that speed is proportional to its distance. Just do the math. You can tell how fast it's going, how far it is. You know from that relation how big the visible universe is, and you know you're looking at 96% of it, that last 4%. Whether you see it or don't, believe me, there's nothing visible beyond it. Hand to God.
So we're calling this the visible universe because beyond that fog, we don't know what's out there on the other side, or through that fog, there could be,
Touche.
okay.
And remember, tonight, we're actually talking about going beyond all of this.
Would that be some billions of light years away then, at that point?
Exactly right. Funny you should say it, because our visible universe, 14 billion light year radius, roughly, don't mind me rounding it off. This object, 96% of that, but 13.44 billion. So this object that you're looking at now was actually born, an entire galaxy created within the first few hundred million years of the universe's birth, which itself is mind-boggling. That was thought impossible, honestly, not just 10 years ago, until photographs like this started turning up, and people went, holy crap. So seriously, we'll wrap up. This is all we can see, and then I just want to quickly go through all we can say, and then we're going to get into it.
If the telescope view was shifted now 90 degrees, would we see another red image like this?
Funny you should ask, because this is something scientists think about all the time. And precisely because of that, the answer is yes. This is the Hubble Ultra Deep Field. Before that, you had the Hubble Deep Field north, and then they took and they shot not 90 degrees, but at 180 degrees opposite the Hubble Deep Field south. And that was what they wanted. I mean, are you getting the same thing? And a bit of a head scratcher is that, yeah, they're close, but I still see papers coming out all the time about little subtle differences that they're still trying to work out and explain. I mean, the theory is they ought to be identical. Same number of galaxies per square degree, same distances.
I guess part of what I'm wondering is, so this guy is going at 96% of the speed of light that way.
Mm-hmm.
Is there something over here going 96% of speed of light that way.
Yes,
And that way.
but don't even think about getting us going on, is that twice the speed of light? Because that's not only special, it's special relativity.
But are you saying then that no matter where you looked with the Hubble Deep Field Telescope, you would see the same view?
Not of the same object, but of the same distribution, the same kinds of objects,
Okay,
absolutely yes.
okay. I thought you were
Absolutely.
saying somehow we had looped our vision, so that somehow it all looked, no matter where you were, it looked at the same thing.
No, you're looking at, that patch, and then that patch, and then that patch, and you're seeing, essentially, ends of the visible universe, pretty much the same stuff. All right, so that's all we can see as of tonight of our visible universe. Let's go to all we can see.
Do they know what that fog's made up out of?
Yeah, it's basically hydrogen.
Okay.
Same stuff our sun formed.
So it's like an
And the
outer
sun's forming
layer that kind of just surrounds us.
Yeah. All right, so as far as all we can see, this is a little bit easier, all we can say, because in fact, all that is known about, everything beyond our own galaxy, that is everything extragalactic, is all research from the astronomical journals, the papers and the data that are collected. They're all assembled in one single place, known as the NASA IPAC Extragalactic Database. The very logical reason that all of the information that we do collect on the visible universe beyond our own Milky Way into one single source is because U.S. federal law, if you're doing astronomical research that benefits in any way from public funding, like Hubble Space Telescope, public funding, then all your results, whatever you publish, must, within a year of that original date of publication, be made publicly available. And the way the U.S. government makes that policy, implements that policy, is that through NASA. The way NASA implements that policy is by contracting 3 large institutions. We've got JPL, the Jet Propulsion Lab in Pasadena, Caltech, who pays my checks, that's the California Institute of Technology, thank you, and IPAC, the Infrared Processing Analysis Center. They're all in Pasadena, California. That's the mecca of extragalactic astronomy since Edwin Hubble's time, which is where he studied. But I just want to make the point, all the information goes from this database because of these U.S. federal laws, and as we speak, the database holds records on 163.2 million objects or galaxies. So it's a pretty big project, but it's like all of us. It's a work in progress. I can remember 15 years ago there was 10,000 galaxy records in this database, and I swear to gosh, I'm promised in 10 years from now we're going to have 100 billion. In fact, roughly a sense of every single galaxy that exists in our visible universe will be in our database. Now, today, the team that goes out and researches the papers and brings in the data and collates and disseminates and makes it available to the public, about a dozen people or so. You can see I'm a member, but by far the most important member of the NED team is Barry Medora. Now, Barry is the Stephen Hawking of this field. Hand gosh, now I've been lucky enough to know Barry for 34, 5, maybe 40 years. I've kind of lost count, but when he was just a young whippersnapper starting out right here in Canada, University of Toronto. And in fact, it's funny, I thank heaven every day that this professional astronomer went on to become a superstar in his field, because as a result, the amateur astronomer you see before you went on to become employed. And what I do with the Fornet, the part I help work on, is I basically keep track of the galaxy distance estimates. I make a tabulation database of the published estimates of the distances to these galaxies. It's basically a small subset of this database. We call it NED-D for distances, galaxy distances. And you can get at the work we do in a couple of buttons. Listen, when I started 5 years ago, I was several pages behind this front page. It was good to have a couple up front. We are expanding, if you'll pardon the pun. Now, I love Barry, but I'm just gonna skip forward here. There's a quick introduction. You can go to our website. I really don't want to bore you with the grisly details, just to say what I work on, along with Barry, myself, the med team. It's about half a dozen astronomers, scientists, engineers, technicians. It's a master list of all of the redshift-independent extragalactic distance estimates and published for these galaxies since 1980. What that entails is it's really, I'm not going to freak you out or anything. All I'm showing is a big list, okay? It's not rocket science. It's basically a table, in fact, a database, and we just start with distance estimate number 1 for galaxy 1, distance estimate number 4 for galaxy 2, and it goes so on down the line until all I really want to illustrate is we've got 36,411 distance estimates for 9,193 galaxies. It's enough distance estimates that for our sister galaxy Andromeda, also known as Messier 31, we've got 100 individual distance estimates for that one galaxy. These estimates, without again getting too gory on the detail, are based on about 4 dozen, hand to gosh, different methods. When I started, I can remember there's basically about half a dozen ways of estimating the distance to a galaxy. This is really an exploding field. You can visit the site, professional astronomers and non-astronomers, everyone. You can click on any one of these, you can see they're highlighted linked, and you go right to a pretty jiffy explanation of what the methods are, how they work, complete with examples of applications in our database, linked right back to the original sources for even more information. But without dwelling, very quick example, let's take type 1a supernova. Some of you have probably heard of these, but in a nutshell, you're just talking about a particular kind of star that explodes at the end of its life. What's interesting for the purpose of estimating distances is that all of these type 1a supernova explosions explode with the same intrinsic brightness. So if you've got 2 of them in 2 different galaxies, and you see that this supernova is 100 times fainter than this supernova, then you know mathematically it's exactly 10 times further. And if you get a distance estimate of the first one, you've got distances to go, so on. Long story short, let's not overstay our welcome on the technical aspects.
Well, if there are so many ways of, there's so many estimations of distance,
So many.
which one's right?
Well, that's what I work on, and now you're just getting cranky, because honest to gosh, you would not believe, they use Fisher matrices and all this stuff, and you wouldn't believe you're comparing a whole slew of different ones. I'll tell you in a nutshell though, there is a trick. If you look closely, we could go back, I won't bore you with it. There's actually not just 4 dozen methods. There's actually 4 dozen methods of 3 primary kinds. You got your standard candles like the supernova, there's certain level of brightness. But you've also got a thing called standard rulers. They're a certain size, like the size of globular clusters. So you can use these to play off of each other and test. Are these things agreeing? If they don't agree, how much by, what amount by, don't they agree in this kind of thing?
So
It's a heck of a question. You're just opening a can of worms.
So it sounds like you can use one to support another.
Yeah, in a nutshell. I'm going to just say that, exactly.
Or verify it.
Yeah.
Can I ask it maybe,
Oh,
sorry, more basic.
Thank you!
I'm startled that you say all supernova are the same brightness when they first explode. That's interesting.
All type 1A supernova are the same brightness.
So it's related to...
Type 1B, type 1C,
Okay.
type 2, whole different kettle of fish. And I've even heard they're talking about now a type 3, which is news to me. But yeah, the type 1A, it's just basically a neutron star that has got a limit of 1.4 solar masses. So they're all going to blow up at about the same...
So it's related to mass, okay.
yeah, it's a kind of critical mass
Right.
sort of thing.
Weren't they pretty rare even? Like, aren't you watching a long time waiting for a supernova to go up?
You can't believe how rare these are. I mean, I've got all the papers going back to, they've been studying these things since 1885. I'm like, what the heck is that? And so rare. The nearest one to us, honest to gosh, is about 10 million light years away. That's how rare they are. So the way to get around that, and the reason I've got now, we have a boatload of these supernova estimates, is because they've taken these, I mean, massive robotic telescopes, a meter across, and they're just drilling through the sky every night. They're going click, 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 and they're looking for any change in brightness, comparing them every 3 nights, and as soon as they get hit, boom, right back there, and then they're putting the Gemini 10 meters in, and cow, they've got a supernova. And that's how they're solving that rarity problem.
Okay.
They're doing massive surveys, because these could not be more important. All the distance estimates that I work with are tending to be pretty accurate, knowing when you're near in. But the only thing that really does go, you can see it right across the universe, are these supernovae. Gamma ray bursts you can see too, but they're not very accurate. These supernovae are really precise, and you can see them right the way across the universe. So a lot of work is going on to getting around that rarity problem and bringing in as much data as you can, because it's really, it's a key to everything. And I just want to add, the reason the distance estimates that we're working on at NED sub-D part are so important. You're looking at Andromeda earlier. Picture any galaxy. Okay, so we know Andromeda, our sister galaxy, is 6 full moons across. But I mean, okay, it's apparent size. If you don't know how far that is, if you don't know that that's 2.4 million light years, there's no way to tell how big the object actually is. We know it's 100,000 light years across, like the Milky Way. So these distances are big difference makers in the field of extragalactic astronomy. I swear to gosh, they are the data that are lifting extragalactic astronomy. I mean, one distance at a time, transforming the field from a science of apparent measurements. You know, you've got the apparent positions on the sky, the apparent diameters, their apparent magnitudes. No. With a distance added to that, you transform these apparent properties into the absolute diameter of the object, into its absolute position, not only in 2 dimensions on the sphere, but in 3 dimensions of space, including depth and distance. Really, really important, and they're also rare. I mean, we've got 163 million galaxies in NED, 9,193 have distance estimates, so basically a very, very small percentage. We husband them and cherish them and wait for more every day. They're very rare and precious. Some of the things you can do with these distance estimates, one, you can make 3-dimensional maps of our Milky Way's position in our local universe. Here's our Milky Way. You saw the satellite galaxies, the large and small Magellanic Cloud. There they are in their true relative positions based on these distance estimates. Here's our sister galaxy, Andromeda, Messier 31 also, with her satellite galaxies and her companion galaxy Triangulum, Messier 33, all in their true relative positions to us. So that's kind of exciting and fun. But the real thing that these distances do, the part that I and my colleagues are really interested in, these distance estimates are the stepping stones, the mile, post-mile markers, if you will. They're the only thing that we have to measure the exact size of our universe. In fact, I showed you Barry Medor earlier. I didn't mention that Barry Medor, I said he's big in the field. This is how big he is. Barry and his wife, Wendy Freeman, were the co-leaders of NASA's Hubble Space Telescope, key project on extragalactic distance. They're the folks that in 2001 discovered that our universe is in fact 14 billion light years in extent, plus or minus 10%. That was these guys. Now, the 10% plus or minus is good, but what we're hoping for with this increasing amount of distances data, Barry and Wendy did their research with a couple hundred distances. We're now up to about 10,000 in the database. And with this massive increase in statistical power, what we're really hoping for is to get the estimated age of the size of the universe to a precision plus or minus 10%, something down to 1%. The reason that extremely highly precise estimate of the universe's exact size is important because there's a lot of people who believe there's a unified field theory, a unified theory of the large and the small, of the universal scale and the atomic scale, a theory that connects all of these. But there's absolutely no way to prove that until you've got an estimate of the size of the universe that is at least comparable to the estimate of the radii of hydrogen atoms, which are known to parts per billion. So we're hoping to get the size of the universe down to parts, oh heck, I'd be happy with 1%. The reason is, some people believe, and I'm not pie in the sky here, it's not blue sky, Sir Arthur Eddington, the astronomer royal, who proved Einstein's theory of general relativity. He did the solar eclipse expeditions that took the photographs of the bending of light rays around the sun in 1919. That, Sir Arthur Eddington said, our universe is as much larger than the individual hydrogen atom as that individual hydrogen atom is larger than its atomic black hole diameter. Now, I just want to knock off the technical mumbo jumbo and go right to why is this important? Because if this is correct, if there is this theory, I believe, Eddington believed, many believe. If it proves true, we need the data to find out. If it does prove true, it could lead to new sources of cosmological energy more powerful than Star Trek's antimatter. Talking about new understanding of the subatomic world that could lead to new materials and new elements, created at will, like Star Trek's replicator, new understanding of the nano world for our health, new powers over the quantum world for our computers, information, entertainment. Now, all these inventions are as close to us right now, maybe 50 to 100 years out, as the Einsteins that resulted from, as the inventions that resulted from Einstein's theory in 1905, were to him. Talking about solar panels right out here that Doug's providing the grid with, the nuclear power that's providing almost half the power that we plug into, the CCDs in our video cameras, and in fact the diodes in our displays. Every one of those resulted from Einstein's theories in 1905. So it's important, but for tonight we're just going to leave the future for the future. I just want to show you what motivates me. Really what's important to us tonight in our idea is not the fact that it's 14.1 billion-year-old universe or 14.23 as some might argue. It's the fact that it's anything. I mean anything at all. I mean if it's X, then it begs the question, what comes after Y? I mean everybody knows space and time are infinite. Any philosopher, scientist, religious leader will tell you that just like that. So then, if the universe is 14 billion light years in extent, well, what the heck? What comes after that? Well, we're going to boil that down, and I think you...
Before you go farther, this sort of theory that our universe is like an atom for another level beyond.
I love this.
Can we go home now?
So that continues.
Are you been looking ahead? What the hell? Yeah, there is. Fine, you should mention.
I have a simple question. Are we de facto at the center of the universe?
That is the standard cosmological model, and it drives people crazy. I mean, it's an illusion by definition. By definition, that is an
An
illusion.
illusion. However, it's how we see it.
It's exactly how we see it.
Tell us.
Pretty much.
My question is, if now that we're given, that we think we know the size of the universe, how significant are we in it? I mean, that sort of begs to the center of, but in the effect, in the context of the things that we know we're doing to our little planet, how far-reaching are those that we know?
I'm going to let Douglas take that one on, but it couldn't be a more relevant or important question, because all this blue sky subject of the universe and our position and all that heavenly thought, when it boils down right down to it, we're all here now on Earth, and we have to make the most out of it. I swear to gosh, if we got blinked out by an asteroid tomorrow, the universe would not care.
Great.
We are the custodians of our own planet and our own life. I would add, though, that I honestly believe, I said in the intro, we're going to tie this up at the end, that if we really want people to take responsibility for the position that we have here on Earth, our custodianship, then we're really going to improve and increase our odds if we all, everyone on planet Earth, whatever religion, Islam, Catholic, Protestant, whatever, if we all agree on our own definitions of what is infinity and what is boundaries and where we are in the big picture. If we can't get the big picture together, I'm concerned that we're never going to be able to deal with these smaller pictures. And I don't mean to make the Earth a smaller picture, but it's damn tiny compared to the universe.
But Ian, I think there's a danger in this whole thought. Because if we think we are custodians, and that's probably true, it leads us to feel that we are also in control. You know, like, I mean, like we can do these things, like we don't have to worry that we're running out of helium because maybe, tomorrow we're going to find another source of helium. And I think that kind of thought has gotten us to where we are now.
I think you make a good point, and I would add to custodians, I mean in sort of custodial sense of a janitor. The janitor doesn't think he runs the school.
No.
The janitor just thinks he's keeping the school running.
Right.
That's the difference.
Yeah.
But it's an important point, and I appreciate the distinction. It is important. And for all of us, I mean, give me a break. I'm fighting ego all the time. You have no idea. I'm always trying to get to the point and cut me out of it as much as possible. It's really not about me.
Right.
And it's really not about us. It's about us together. So,
Quick explanation of atomic black holes. Are you suggesting subatomic black holes that exist amongst us?
yeah, I hate to tell you. Well, I'm not in the Stephen Hawking camp that, there was one of them. I am of the camp that this is as much smaller than that atom, if it were there, as that atom is smaller than the universe, if it were there. I just want to make the mathematical connections. And so, and I kind of want to get to what you were saying about so I just want to, again, get to the definitions of infinity and boundaries. And we're kind of at that tipping point now, because beyond our own universe, 14 billion years, what comes after that? And I think you'd be surprised at how limited the possibilities are. In fact, beyond our universe, one, there is A, nothing, or B, something. I don't think I've left anything out. I would love, honestly, by a show of hands, to know amongst the members attending, do you think that beyond our universe there is a, and if you do go ahead and say nothing, I swear to gosh, you're right in league with all of the smartest people on our planet right now, because today's standard cosmological model posits, look in the textbooks yourself, that our own universe is expanding into empty space. Absolutely nothing. So hands up everybody who thinks that beyond our universe there is absolutely nothing. Takers? Anyone? Gary? One? And who here thinks beyond our universe there's got to be something? Yeah, that's kind of, not to be disagreed, that's how I feel too. That's my exact thought. It can't be nothing because, well, there's, in our lives as we go through day to day and all these things come up, and I always joke, it's always something because there's never nothing. There's no such thing. There's just no such thing as nothing in our universe. They look for as close to a vacuum as they can get. They've never found it. They never will. There's always something. Well, if we do agree, everyone except Gary, and I'll get you before you end the show.
Can we stop there for a minute?
Please.
If you go back to the very beginning, before everything started to expand.
Go ahead, Nels, here we go. Go ahead.
So what was there for it to expand into at that time?
Now
Was it nothing?
you're making me crazy because the standard cosmological model, the technical answer to your question, if I go to the textbooks, I open them up, hand to God, not only is it expanding into nothing, true, but without a word of a lie, I'm not making this up, the whole thing exploded out of nothing. I am absolutely not kidding you. And it makes me crazy because any Greek will tell you, you cannot create nor destroy matter. Any scientist will tell you, conservation of energy, give me a break. You can't create something out of nothing. That's Hawking's view. And I tell you, for a guy that used to be so the damned establishment of the field. Now, I love him because he's a popularizer and he helps raise funds, and those trickle in small part down to meeting my friends, colleagues. But believe me, his physics just absolutely is head scratching, frustrating, because it can't start with nothing. But does that answer the question? Does that sort of show you where we're at in terms of the forefront of physics?
Well,
Maybe not as far as you might think.
Well, it makes it difficult to answer that question because we're still expanding, are we not?
So they say.
Really, we're still expanding into what we were expanding into when we first started.
Bingo.
So what was
Give you two quick ways of looking back at it. When Edwin Hubble first saw these galaxies pushing away from each other, they just talked about running the movie backwards, which is exactly what you just said. So you're just running back, and there's a couple of ways that people have tried to get out of this, but it is a head scratcher, believe me. You go backwards, and you can imagine it just getting slower and slower and slower, so that it never comes to the beginning. Thank gosh. Or you can just go hook, line, and sinker, in for a penny, out for a pound with the standard model, and it does go all the way back to zero. Starts from nothing. Promise, that's not really what's happening. And everybody knows this, but the physicists have not, amongst themselves, the smartest people on the planet, have not been able to agree on what to replace that. Understandably inadequate.
Not the theologians.
I'm calling them today because I'm furious. I'm not going to take this anymore. So we're back up to beyond our universe. There is, well, everybody's in favor of something except for Gary. We'll work on him. If there is something beyond our universe, then again, I think you'd be surprised at how limited the possibilities are. I mean, A, it's something completely different. I don't mean to be Monty Python-esque. But the only possibilities are something completely different. It's not made of matter, not made of energy, it's not atoms, not protons and electrons, it's not anything we recognize. It's something we may not even ever be able to understand. Or B, it's just more of the same. Not rocket science, it's just going to be more matter, more energy, more of the same. Ad infinitum, on and on, infinitely. So I've got almost everybody up to beyond our universe. One, there is be something. So by a show of hands, I'd like to see now what that something is in our collective opinions. There is A, something completely different. Who thinks it's completely different? We'll never understand it. Got some takers. Okay, a little more division here. And who thinks B, it's just more of the same, more matter, more energy, just goes on and on and on.
Or a combination of both.
Well, it's funny you should say that. I'm the biggest believer in the possibilities of the combination of both. In fact, we're talking about infinity and boundaries, and everybody says, oh, it's going to be one or the other, it can't be both. Well, hey, as a matter of fact, let's get to what you were talking about, because I'm going to go with this route. Beyond our universe, one, there is B, something, and two, there is something that is more of the same. And if that's the truth, and I'll just illustrate what I came up with, just for tonight, I want to show you this. Now, this is not original. This is an old idea of the Greeks. I mean, you just brought it up. Atoms within universes, universes within atoms. Not rocket science. It's an old, brilliant idea. Now, in defense of humanity for not getting this together more quickly in the last 2,000 years since the Greeks, this is, I must admit, the best illustration I've seen of this theory, and I studied this field night and day. What I want to show is this is our universe right here. Sorry to call it universe one, that's just a little universe-centric on our part. But in a nutshell, our universe is really 14 billion light years across, just one of a whole slew of universes, all side by side, going on, word onward, and infinitum, infinitely to the left, infinitely to the right, infinitely up, infinitely down, infinitely forward, infinitely back. Just a pile of universes. In fact, that pile makes it look kind of like atoms. I mean, this is exactly what a bunch of atoms of atomic angstrom diameters would look like. And in fact, it's funny to do because you can picture our entire universe here as just a single atom here inside of a larger universe, shown right here. In fact, this larger universe that our universe is an atom within is itself just an atom in an even larger universe than that. And this just continues onward and upward to ever larger and larger sizes. Well, conversely, you go downward to ever smaller and smaller sizes, and if you look closely at our own universe, the universe is like it, here you can see we show the individual atoms. And each one of those atoms, right here, right now, itself may contain an individual universe. Within that individual universe right there are more atoms, even smaller, and each of these contain their own universes, and onward to ever smaller and smaller sizes. Well, this is a broadening of our definition of infinity, because infinity is, we normally think of it, 3 dimensions. Yeah, these universes, all the same size, go onward infinitely. To the left, the right, front, back, up, down. What we're talking about is a somewhat broader definition, because they go upward in size to larger and larger scales. And then a third definition, they go downward in size, inward, smaller and smaller scales. So that's a little bit more about infinity than we've historically had. And I just want to try and sharpen our definition of boundaries.
Can I interrupt there?
Please.
Are there, since you've touched on boundaries now, in your description of universe 1, and then there's 2, and then there's 3, and then there's a gazillion, are there boundaries between them? Is that, well, I guess that's what you're going to get at, right?
That's exactly what we're interested in, and defining those boundaries.
So how do we know then, or do we know where one stops and the other one starts?
First way, every single line on this illustration is a boundary. So around every universe, of every scale, large and small, is a boundary.
The Dark Ages cloud.
Bingo. That's right. There's a boundary of our universe. And it's a fact that it's a boundary because we can never go beyond the limits of our own visible universe. We just can't. And in fact, these lines here, the atoms in our universe, we can never go through those individual atoms. That is a boundary we will never, ever penetrate. Similarly, this giant universe, containing all of these universes, within all of these atoms, within all of these universes, that is a boundary. Every line on here is a boundary. And I would just add that in our own minds, it's size dependent, because we're sitting inside this room, on our planet, in our galaxy, in our universe. And we look up, and we see this big boundary. You were kidding earlier about fog. But that's it. That's the boundary of our visible universe. We don't see so clearly. If we look down here, sure, we can split atoms apart, but they'll just come back together again into hydrogen as quickly as possible. And there is no way anyone is ever driving a spaceship, I don't care what Star Trek says, through that atom. Those are little boundaries. So we have big boundaries, universes, and little boundaries, atoms. The main point is, it's just a recurring pattern. It's basically a fractal. This isn't rocket science. Fractal patterns occur on the beaches and trees and plants. You see them everywhere, and it would, if anything, be surprising if the universe didn't work this way. You're simply seeing a pattern repeat itself over and over and over again in size. It's just a size difference. It goes from atoms at the small size to universes at the big size.
Is it always